So we start application of derivatives, and we know there are a number of application of derivatives. Okay, it's not just a few. Say some of the most important applications. Can anybody recall what are some of the most important applications of derivatives in physics? In physics, what are some of the important application of derivatives?
For finding velocity and acceleration.
Yes, so this is rate of change. We call it as the rate of change, or we mention as the rate measure. So this is one of the most fundamental, and incidentally, in general aptitude, we will be using this. When we do general aptitude, that's when we will discuss problems related to these rate of change, rate measure. And this is a very important application of derivative. It is not just for speed and velocity and acceleration of any objects, but it is also for volume changes or any rate of change. Then in numerical methods, very important is errors and approximations. Errors and approximations. This is one of the very important application, errors and approximations. And any engineering computation, when we have to do numerically, we have to understand that there are errors and how to estimate the errors. So this is very commonly used. Then we have tangents and normals of curves. This is within mathematics, tangents and normals. Then we have mean value theorems. They are mean value theorems based on application of derivatives. And where are these mean value theorems used? They are mostly used in identifying roots of equations. Then an important study is monotonicity of functions. Then very important, maxima and minima. These are the functions, and of course, further applications of derivatives you will see in curve tracing, tracing of curves. So these are a number of applications. Now, from the perspective of gate, see these rate of change and errors and approximation, pretty much they come in general aptitude. Tangents and normals and mean value theorems, they come not in great frequency, but some questions come from these. Monotonicity of a function is something very important we need to understand to study the nature of functions. Although by itself we don't give importance to monotonicity, it is very useful for finding the maxima and minima of functions. So this is very important. Again, curve tracing is also important, but curve tracing we will do when we do areas under curves by integration and volumes. So that time we have to know curves, and that time it is not just the Cartesian curves in X and Y. We also have to draw curves which are defined parametrically. So at that time, curve tracing, when we study curve tracing, it will be very useful for what we do. So as of now, what we are going to study is pretty much tangents, normals, mean value theorems. We'll touch upon monotonicity of functions and maxima and minima. So this is what we are going to study here. So here is the first topic, tangents and normals. So simple, let us first plot a curve. So let's say we have a curve. Some curve like this. Now, at a point on the curve, some point P on the curve, all right, we can draw a tangent to this point. Okay, these are, I'll draw it again. Freehand is better maybe. I draw a tangent at this point P on the curve. Okay, and at that same point P, I draw a perpendicular, a normal. So this point PT is called as the tangent or the length of the tangent. Pn is called the length of the normal. All right. Now, so let this curve be y equal to f of x. So y equal to f of x at P is some point, say x1, y1. So slope of the tangent to the curve y equal to f of x at P x1 comma y1 is m is dy by dx at that point x1 comma y1. So from the basic derivatives, the definition of derivatives, we understand that the derivative is the slope of the tangent at that point. Derivative at a point of a function is the slope of the tangent drawn to the curve of the function at that point, as long as the function is differentiable. If the function is not differentiable, this question doesn't arise. So this is the slope. Now, equation of the tangent. Equation of the tangent is y minus y1, point slope form of the straight line, and y minus y1 is equal to m into x minus x1, and this m is dy by dx at that point P. So this is the equation of the tangent. Equation of the normal. What will be slope of the normal? Because normal is perpendicular to the tangent, equation of the normal will be minus the reciprocal of the slope of the tangent. So minus dx upon dy. This is the equation of the normal. And then there is a subtangent, length of the tangent, length of the normal, that we can find out. If I have to find out this. Now this angle is theta. Now tan theta is, I drop a perpendicular from here. I'll call this S. So tan theta will be PS upon ST. And sin theta will be PS upon PT. And what is PS? PS is this value y. It is the y coordinate. In fact, the curve can be below the x-axis or below the. So in any case, we just write this as y1 upon pt. Now let's say tan theta is m, slope. Tan theta is the slope of this line, and slope of this line is the tangent to the curve, so that will be equal to m. All right. So tan theta is this. So sin theta by trigonometric ratio, if tan theta is m, sin theta will be m upon root of 1 plus m square. So pt, this is the length of the tangent, y upon m into root of 1 plus m square. This is the length of the tangent, we call. Tangent from the point on the curve to the point where it cuts the x-axis. This is the length of the tangent. Similarly, we can find the length of the normal. So to find the length of the normal, this is 90 minus theta. So again, take tan of 90 minus theta is PS upon PN. From this triangle, tan of 90 minus theta is PS. I'm sorry, it should not be tan, it should be, I want PN, so it should be opposite side by hypotenuse, so it should be sine. Just a sec. Sine of 90 minus theta is PS upon PN. So we get cos theta is PS upon PN. So PS is Y1. Cos theta will be 1 upon root of 1 plus m square, because tan theta is m. Cos theta will be 1 upon root of 1 plus m square. So what we get is length of the normal. Length of the normal, Pn, is y1 into root of 1 plus m square. Of course, because we are talking about lengths, we must emphasize here that we'll have to take modulus, because we have to omit the sign when we talk about lengths. Now, why am I going through this? Because in differential equations, it will be very, very useful. Length of the tangent, length of the normal, equation of the tangent, equation of the normal. You get many questions on differential equations centered around this. Today, we'll take a very simple example, not it is not so intricate differential equation solving, but something very simple based on this concept of tangents and normals. Next, there is something called as subtangent and subnormal. ST is called as subtangent length and SN is called as the subnormal length. So from this equation here, the equation that we have here, ST is PS upon M. Very simple. So subtangent length ST is here. So this length ST is called as the subtangent length, SN is called as the subnormal length. So ST is PS upon M, so Y1 upon M. And because it is length, we take the modulus. And subnormal SN, we take cot. Now we take 90, tan of 90 minus theta is PS upon SN. So cot theta is PS upon SN. So SN will be, I'll just write here, so that tan of 90 minus theta is PS upon SN. So this is cot theta. So SN will be PS upon cot theta, which is PS tan theta, which is PS is Y1, tan theta is M. Okay. So this is, I will write here Y1 into M. So these are the four results of tangents and normals. So we can find tangents to the curves through this. Application in curves and intersection of curves is in finding the points of the angle of intersection between two curves. Angle of intersection between two curves. Okay, the angle, okay, this angle is defined as the angle of intersection between the tangents of the two curves. So we have the first curve here, let's say, and there is a second curve like this, or like this. Now both of them intersect. Now here important, the angle of intersection between the tangents of the two curves, I'm highlighting here, at their point of intersection. This is very important. So at the point of intersection, let's draw tangents. So this is tangent to the first curve, and this is tangent to the second curve. Now the angle between these two is the angle between the curves. So if the first curve is y equal to f of x, and the second curve is y equal to g of x. So how to find the angles? So m1 is dy by dx for the first curve. That means df upon dx, all right, for the first curve. At what point? Let's say this is the point of intersection, P, x1 comma y1. So at P, m2 is dg upon dx at P. And what is the angle? Theta is tan inverse of. Now, if you want to find acute angle or obtuse angle, you can. If you want to choose the acute angle between the lines, then we need to take the modulus. Otherwise, you just leave it like this: m1 minus m2 by 1 plus m1 m2. This is the standard angle between two lines. That result. All right. Now, if m1 m2 is equal to minus 1, then the curves are set to intersect. The curves are said to intersect orthogonally. Okay, so these are some points for us to keep in mind. Now let us do some simple problems. Okay. Let's do some examples before I give some problems on class time. Find the point on the curve y is equal to x cube minus 2x square minus x, at which the tangent line is parallel to the line y is equal to 3x minus 2. So we need to find a point on this curve. Curve is x cube minus 2x square minus x. So it's a cubic equation. Now, at which the tangent is parallel to y equal to 3x plus 2. That means, what is the slope? Slope of the line. The slope of the line y equal to 3x minus 2 is 3. Now, let p x1 comma y1 be any point on the curve. On the given curve. Now, let's say if tangent at P is parallel to the given line, if tangent at P to the curve is parallel to the given line, then what? Then the derivative at P to this curve should be equal to 3. So this is what we'll do. So now, so this implies, what is the derivative now? 3 differentiate y equal to x cube minus 2x square minus 1. So we get 3x square minus 4x minus 1 at x1 comma y1 at P should be equal to 3. Let's substitute. We'll get 3x1 square minus 4x1 minus 3, sorry, minus 1 is equal to 3. So what do you get? 3x1 square minus 4x1 minus 4 is equal to 0. So now let us solve this. This is 3 into 4, 12. So with 12 as the factor, 12 as the product, we need the factors to give the sum as minus 4. The product is minus 12. So it's product of the extreme coefficients. So obviously we get the, for minus 12, we get minus 6 into 2 also gives minus 12. So this is these are the factors. So upon factorization, we get, of course, in the question, he has not given the interval. So let's see. So we get 2 points, which implies x1 is equal to 2 or x1 is equal to minus 2 upon 3. Therefore, y1, x1, y1 lies on the curve. y1 is x1 cube minus 2 x1 square minus x1. Now, if x1 is equal to 2, y1 is 2 cube minus 2 into 2 cube, 2 square minus 2, you get minus 2. If x1 is equal to minus 2 by 3, y1 is minus 8 upon 27 minus 2 into 4 upon 9 plus 2 upon 3. We can simplify this. 27 minus 8, 9 into 3 is 27. So 4 into 3, 12 into 2, 24 plus 18. So we get minus 14 upon 27. So therefore the 2 points are so the points on the curve are 2 comma minus 2 or minus 2 by 3 comma minus 14 upon 27. So there are 2 points on the curve which will have tangents parallel to the line y equal to 3x. Y equal to 3x minus 2. Okay. So this is how we do. This is the application. The concept was very simple. Other things was calculation. What was the concept that we applied? This one. That the tangent at that point should be equal to 3. Others were calculation only. Okay. Next, another problem we'll do. Another example. Find the point on the curve y minus e power x into y plus x equal to 0, at which the tangent is vertical. Find the point on the curve y equal to e power xy plus x equal to 0, where the tangent is vertical. How to do this? Vertical tangent means what will be the slope? What will be the slope for the vertical tangent?
0.
No, that is horizontal tangent. When tangent is horizontal, the slope will be 0. When the tangent is vertical, what is the slope of y-axis?
Infinity.
Infinity. That's right. So, infinity. That means the reciprocal of the slope should be 0. So, dx by dy should be 0 in this case. So, let us anyway try this. Best is what to do. You want to find dy by dx. Differentiate implicitly. So y minus e power xy plus x equal to 0. This is not an explicit function, and it is not easy to make it as explicit function of y in terms of x. It's very difficult. So differentiate implicitly. So we get dy by dx minus e power xy into derivative of xy, and the derivative of xy will be this is product. So differentiating x, keeping y constant, so 1 into y, plus keeping x constant, differentiating y, plus 1 equal to 0. Now let us look at this. So collect dy by dx terms. We get 1 minus x into e power xy plus 1 minus y into e power xy. Now dy by dx is 1 minus y, sorry, it's the other way, y e power xy minus 1 upon 1 minus x e power xy. So for dy by dx to be infinity or dx by dy to be equal to 0, this denominator term should be 0. So 1 minus x e power xy should be 0. Okay, 1 minus x e power xy should be 0. This is little difficult. Let us see. X e power xy equal to 1. So xy e power xy, sorry, is equal to 1 upon x. Taking log on both sides, minus log x. So y is basically so it's not a function, by the way. This is not a function. We want that there is a point x comma y which satisfies this equation. X comma y satisfies this equation, this implicit definition. This is, so this is not an equation, this is not a function. It is like this expression is equal to this expression. So from the given options are of course not, I didn't give the options, but the one of the options given is x equal to 1 and y equal to 0. When you do x equal to 1 and y equal to 0, we get this. Otherwise, this is a very difficult function to plot. All right, e power xy. This equals 1 by x. So, but this satisfies, if you can see here, when x equal to 1 and y equal to 0, this equation satisfies. Otherwise, it's a very difficult equation to solve. At this point, now let us see whether this x equal to 1 and y equal to 0 lies on the curve. If you see here, if we substitute 1 comma 0, so y is 0, e power xy, e power 0 plus 1. So e power 0 is minus 1. So this is satisfying. So 1 comma 0 is a point on the curve. 1 comma 0 is a point on the curve. And at that point, the tangent is vertical. At the point 1 comma 0, the curve has vertical tangent. So of the given options, the options were 1 comma 0, 0 comma 1, 2 comma 0 and 1 comma 1, and you can substitute and see most of them won't lie on the curve itself, but this will lie, and this equation has to be satisfied. So this would be satisfied by 1 comma 0, x equal to 1 comma 0. So this is one. A last example on tangents and normals. Sorry. Is finding the angle between the curves. So if the angle between the curves y equal to a power x and y equal to b power x is theta, then tan theta is equal to options modulus of log a minus log b by 1 plus log a log b, log a plus log b by 1 minus log a log b, 1 minus log a, sorry, 1 plus log a log b by log a minus log b, 1 minus log a log b by log a plus log b. So these are the four options. Which one is correct? So I'll solve this. Say y is equal to a power x. Derivative. Okay. So let y equal to a power x and y equal to b power x intersect at p. Now what will be this point p? X1 comma y1, let us see. So where do they intersect? You get a power x is equal to b power x. So a power x is equal to b power x. Where will they intersect? A power x is equal to b power x. When is it possible?
X is equal to 0.
Very good. If a and b are two positive and different numbers, this will imply that x equal to 0. So when x equal to 0, this will imply you substitute x equal to 0, a power 0 is 1, b power 0 is 1. It means y equal to 1. Therefore, the point of intersection is P 0, 1. Point of intersection is P 0, 1. Now, differentiate. Now consider the first curve. Let M1 be the derivative of this curve at P. So what is derivative of a power x? It is a power x log a. At what? 0, 1. So substitute x equal to 0. Y term is not there anywhere here. When x equal to 0, you get log a. All right. Similarly, y equal to b power x. Now let m2 be the derivative of this function at p. So we get b power x log b at this point 0, 1. Again, we get log b. So m1, m2 is log b. So what is tan theta? Is modulus of m1 minus m2 by 1 plus m1, m2. So we get log a minus log b by 1 plus log a log b. So which is the correct option? The first option is correct. So I did 3 examples. Now I want you to start class time. Okay. So I think, so this is the session. And sorry, it is asking some things. I'll do it again. I don't know why it's asking. So many, yeah. So many. Cross checking. Okay, I'll work out with something else. All right, were you able to log in? All Z449GY. Z449GY. All capitals. Only 6. Out of 16 participants, 15 participants, only 6. What about others? Same, are you facing the same problem or something? I'll try class time and others. Okay. This was what? Z44449 GB. Okay, I'll open the session. I don't remember which one was which question. Tangents and normals. No, this is mean value theorems. So I think this was tangents and normals questions. Yeah. So look at this question, you can answer. If at every point of a certain curve, the slope of the tangent is equal to minus 2x upon y, then the curve is a straight line, a parabola, a circle, an ellipse. There's a question. So please answer. By the way, these are gate questions. The questions that appeared in gate. Okay. Try. Another 1, 2, 3, 4, 5, 6 students attempt. One more student, last student, you please answer your question. No matter if, even if it's wrong, doesn't matter. Now, let us see. Good. Good. Some of you have got this right. See, what is given is dy by dx is minus 2x upon y for every point. Now, this is what I told. There's a problem of differential equation, a simple problem. So, y dy is minus 2x dx. When we integrate, what do we get? Integrate both sides. We get y square upon 2 is equal to minus x square and plus c. If you miss this out, I think most of you have missed this out. This constant you have missed out. When you integrate, we get a constant. So upon integration, we get this. So now we get x square plus y square by 2 is equal to c. This is now of the form x square by c plus y square by 2c is equal to 1. What is this? What is this curve? What does this curve represent? Anybody?
Ellipse.
Ellipse. Yes. So this is an ellipse. That is the answer. So if you miss out this constant, integrating constant, you may get lines. Y equal to root 2x. That's what you will get. And I think most of you have done that mistake. Let us see. So 5 students gave answer a straight line. 4 have given parabola, 1 has given a circle. So 2 have given a circle. So there must be an integration, you must have made a mistake. Clear? So this was that question. Next, tangents and normals. I think the 5th and 6th questions are tangents and normals. So look at the next question. Yes, look at this question. The angle of intersection of the curves x square equal to 4y and y square equal to 4x at 0, 0. Please do this. Good. Please try. Yes, good, good, good. Four more students. Meaning, if you don't have to apply derivatives, apply just common sense logic, you will get the answer. I'll wait another half a minute. Good. One more. All right. All right. Good attempt. And some of you scored correctly. Let us see how we. Now, the angle of intersection between the curves. Now, there are two curves. The first curve is x square equal to 4y. So when we differentiate this, 2x is equal to 4 dy by dx. So dy by dx is x upon 2. Now dy by dx at 0, 0, this is the point of intersection, is 0. So this is m1. Okay. Now, second curve is y square equal to 4x. So at 0, 0, 2y dy by dx is equal to 4. Dy by dx is 2 by y. Now, at so m2 is dy by dx for this curve at 0, 0, which becomes 2 by 0. It's undefined quantity. So this is horizontal slope and this is vertical slope. So this is slope of a vertical horizontal line, this is slope of a vertical line. So the angle between them is 90 degrees. Another very common sense way of doing it, just a very simple common sense way of doing this problem, is that these two both represent the equations of parabola. Y square equal to 4ax is a parabola like this. All right, whose axis is the x-axis and this y-axis is the tangent at the vertex. And x square equal to 4y is a parabola like this. So, okay, not accurately drawn, but yeah, this is the one. So at 0, 0, one tangent is the x-axis, other tangent is the y-axis. So angle between the angle of intersection of these curves at this point. There is another point at one, I think at 4, 4, they intersect. At that point, it is different. At 0, 0, the angle of intersection is 90 degrees. Is that clear? So next question. We'll move to the next. So one was on angle. This is similar to the first question we solved as an example. The tangent to the curve y equal to x log x is required to have an inclination of 45 degrees with the x-axis. The coordinates of the tangent point would be good. Good. More number of students to answer. Very good. Good. Everybody is marking this correct so far. Six more students, please answer. 3 more students. Half a minute more, I'll give. Good. All right. Okay. 50%. Half of you have marked correct. Now, if you are getting it wrong, we should just be thoughtful. Like, why are we getting it wrong? There may be some conceptual error or some thing that we have not paid attention to. That's all. So y is x log x. Now this is product of two functions. If you differentiate first function into derivative of the second plus derivative of the first function into the second, so you get 1 plus log x. Now dy by dx at some point p has a value of tan 45 degrees, because the tangent should have an inclination of 45 degrees. That is the given question. So that means 1 plus log x is equal to 1, which implies log x is equal to 0, and log x becomes 0 when x is equal to 1. And when x is equal to 1, y is x log x, which is 1 into log 1, which is again 0. Therefore, the point is 1, 0. This is the answer. The point is 1, 0, and that's okay. So that's about tangents and normals. And these are questions typically of this type that come in GATE. These are not like very frequently asked, but sometimes they ask, and when they ask, it is not that we should fumble. These are simple concepts of differentiation and their applications. So we should be able to do it. So just go through where is that you made a mistake, and next time you avoid that by practice. So this was about tangents and normals. Next, what we do is mean value theorems. And they are very important mean value theorems. If you go through the notes that I've given, it's very important notes. First, these three that we'll discuss. The mean value theorem. So first, Fermat's theorem is not generally called as the mean value theorem. It is, but we can classify. Now, Fermat's theorem, it says that if a function y equal to f of x is continuous and differentiable in a closed interval ab, maybe I'll do like this. I'll do individually. That will be easier. I'll be able to explain with figures. So the first of the theorems is the Fermat's theorem. And so if the function y equal to f of x is continuous and differentiable, in the closed interval AB, and has a maximum or a minimum value at an interior point x0, then necessarily f dash x0 should be 0. So what this theorem states is this. I'll give it in a very simple example. Now, these are 2 points A and B, and function is continuous and differentiable in this. Continuous means there are no breaks in the graph. Differentiable means there is smooth curvature. There is no abrupt change in the curvature. So now, suppose you have a graph of the function like this. Now, what it says is, if the function has a maximum or minimum value at some interior point x0, so here we see in this vicinity, this is the maximum value. At this maximum value, you look at the slope. The derivative will be 0. So this is some point. What, according to Fermat, this is, say this point is x0. If it is a maximum, then the derivative will be 0. Similarly, if it's a minimum, here this is a local minimum, so derivative will be 0. So what we use the concept of derivative being 0 for maximum and minimum. It is actually coming from Fermat's theorem. All right. Fermat's theorem is very simple. If derivative is 0 at a point, that point will be a maximum or a minimum. Next, a very important theorem is Rolle's theorem. Very important theorem. Very often quoted and used. So if a function f of x satisfies 3 conditions, observe these very, very carefully, the 3 conditions. It is continuous and closed interval AB. It is differentiable in open interval AB. And at the extreme ends, the function values are equal. Then there exists at least one interior point C where the derivative becomes 0. So now let us study this. Rolle's theorem. This is a easy theorem to understand. It's not a difficult one. Now f of A is equal to f of B. All right, this is the third condition. Function values are equal. Function values are equal. F of A is equal to f of B. Now the function is continuous in this interval. That means if I join this point to this point, I should join with a curve which has no breaks. Second, it has finite derivatives, which means the derivative never goes to infinity, and throughout function is differentiable. So now I have to join these 2 points. Now I can draw a curve. This can be a curve, the yellow line. So the function increases, then reaches a peak point and then decreases. So at this particular point, derivative will be 0. Clear? So if two function values are equal at the extreme ends of an interval, and in between the function is continuous and differentiable, then definitely there will be a point where derivative is 0 inside. It is at least 1 point. Why at least 1 point? You can have more than 1 points. Let us look at this one. I have to join this points. Let me call this as A and B. I have to join these points A and B with smooth curve. And here I have drawn a curve like this. So here you will have horizontal tangent here. So derivative is 0 here. Here also you will have horizontal tangent, derivative 0. Here also horizontal tangent. So we have 3 such points here for the second curve. Clear? And you can increase, there can be infinite number of points, depends on how the curve is. For example, if you take sine x from 0 to 20 pi, then each time it will have like between 0 to 2 pi, you have 2 points of one maximum, one minimum at 90 degrees, and that is at pi by 2 and 3 pi by 2, maximum, minimum. So into 10, so 20 such points you can get. So this is the point. Rolle's theorem says if a function is continuous on closed interval AB and differentiable on open interval AB, and function values are equal at A and B, f of A equal to f of B, then definitely there will exist at least 1 point where the derivative is 0. So this is called the Rolle's theorem. All right. Next is the extension of Rolle's theorem. And this is very popular, and this is known as the mean value theorem. Although the others are also mean value theorems, Rolle's theorem is a mean value theorem, but this is the general mean value theorem, Lagrange's mean value theorem. The difference between Rolle's theorem and Lagrange's mean value theorem is this. In Rolle's theorem, there are 3 conditions. In Lagrange's mean value theorem, there are 2 conditions. The third condition of Rolle's does not apply here. What it says is the function f of x is continuous in closed interval AB and differentiable in open interval AB. Then there exists at least 1 internal point C in the open interval AB, such that f dash C is f of B minus f of A by B minus A. What does this mean? Let's look. So let us say we have AB. Now f of A is not equal to f of B. So let's say f of A is here and f of B is here. Let us take these 2 points, A B. What are the coordinates of these points? A is A comma f of A. What are the coordinates of the second point B? B comma f of B. What is slope of AB? F of B minus f of A by B minus A. So this right hand side in this mean value theorem is nothing but the slope of the line joining these endpoints of the interval A and B. All right. Now, function is continuous and differentiable. So I have to join this point A and B by a smooth curve, which will not break anywhere. And it should be, the curvature should be smooth. So let me draw some curve. Okay. Let me draw some curve like this. Okay. First I'll draw a curve like this. Now what this mean value theorem says is, Lagrange's mean value theorem, there will be one point C where the tangent to the curve will be parallel. This is the tangent to the curve. This is parallel to this chord AB. All right, that is what Lagrange's mean value theorem is saying, and which is true. There will be at least one point when you try to join AB. There will be at least one point where this f dash c. So tangent, or I should say slope of the tangent, at C is equal to slope of the chord AB. So now, no matter what kind of curve we choose, we will get this. I'll have to choose a lighter one. I'll use this. Okay. It need not be just one point. It can be 2 points. It can be 3 points. It can be infinite points. Depends on how you choose the curve. Okay. So here these tangents are parallel to this chord AB. Now Rolle's theorem is just a special case of the mean value theorem, where f of A and f of B are equal. If f of A and f of B are equal, what happens is the chord, let's go back to Rolle's theorem. So if f of A and f of B are equal, the chord joining AB, it's already a horizontal line. So therefore, the derivative must be 0 in that case. In Lagrange's mean value theorem, it is not that. It is that slope of the tangent to the curve is equal to the chord, the slope of the chord. Now, there are very useful questions from these mean value theorems. We will just see. Okay, I'll go to class time. We will solve those questions. Go to the first question in class time. So go and select the first question. Okay, I'll solve this in class. I'll ask you to solve the other ones. You just look at this. I will do this example. A function y equal to 5x square plus 10x is defined over an open interval 1 comma 2. At least at one point in the interval, dy by dx is exactly this. So what it means is, this is f of x, 5x square plus 10x on 1 comma 2. So now what is f of 1? 5 into 1 square plus 10 into 1, which is 15. What is f of 2? 5 into 2 square plus 10 into 2. So 20 plus 20, 40. Now there will be at least one point by Lagrange's mean value theorem. There will be at least one point where derivative is equal to the slope of the chord joining the extremes, f of 2 minus f of 1 by 2 minus 1. So we get 40 minus 15 by 2 minus 1, which is 25. This is the answer. Okay, so we can 25. This is the correct answer. So now I'll give you a chance to do the other questions. Question number 3. Look at the question number 3. This is the question. I'll give you 5 minutes. 5 minutes. Usually I give 3 minutes. I'll give you 5 minutes to crack this. I give you 1 more minute. Good. Good. All right, time's up. Let's do this. See, look at this. Others can also answer and keep it. Okay, just look at this. What it says is f of 0 is 2, and we have to find the upper and lower bounds. That means highest and lowest values of f of 1 estimated by the mean value theorem. What mean value theorem says is there will be at least one value, say one value where the derivative, one value of x where the derivative will be equal to the slope of the chord. So given as f of 0 and f of 1, okay, f of 0 and f of 1. So which means then we'll have to take these two as the extreme points and apply the mean value theorem. Okay, this is the Lagrange's mean value theorem. So f of x is 1 by 5 minus x square. This is f of 1 minus 2 by 1, which means f of 1 is 2 plus 1 by 5 minus x square. So from the equation now, x, we are discussing which interval? 0 to 1. X has to lie between 0 and 1. It cannot cross 0 and 1. Why? Because we are applying Lagrange's mean value theorem within this interval, 0 to 1. F of 1 is the extreme, f of 0 is the left extreme. So now clearly this value f of 1 has to be greater than 2 because it is 2 plus some positive quantity, because x lies between 0 and 1. So either second or the third option will be right. None of them also can be right. So let us see. Now, if you put x equal to 0, you will, between 0 and 1, if you put x equal to 0, the denominator will be maximum and the reciprocal will be minimum. So put x equal to 0. So f of 1 will be 2 plus 1 over 5, which is 2 plus 0.2, which is 2.2. Putting x equal to 1, so within this interval 0 to 1, 1 is the maximum value. So the denominator will be least. Two plus 1 upon 5 minus 1, 4. 2 plus 1 upon 4 is 0.25. So 2.2 to 2.25. So this was a previous year's GATE question. applying the lower bound and upper bound. What could be the maximum or minimum possible values of f of 1? So just by logic, we have to do. Up to here, everybody must have done it. I have no doubts about that. Okay, most of you must have done it up to here. After here, you just have to identify which is how you will find the lower and upper bounds. For that, we have to understand that we are applying on the interval 0 to 1. That's it. Okay. Then the last question for today on mean value theorems. Hmm. 5 minutes. I'll give you just 2 minutes time. Please answer. Good. 2 correct answers. Okay, I'll stop now. Please, most of you have done correct. Good. Most of you have done correct. Excellent. So, okay. So look at this. So f of x is capital A x square plus bx plus c. Now f of a is capital A small a square plus capital B small a into c. F of b is capital A b square plus capital B small b plus c. Now what is f of b minus f of a by b minus a? You get a square plus ba plus c minus of, a b square plus bb plus c minus of a square plus ba plus c by b minus a. C and c cancels. We get a into b square minus a square plus b into b minus a by b minus a. So this is a into b plus a plus b, because b square minus a square is b minus a into b plus a. Okay, so this is what we get: f of b minus f of a by b minus a. Now what is, now given f of x is ax square plus bx plus c, what is f dash x? F dash x will be 2 capital AX plus B. Now f dash of epsilon will be 2 capital A epsilon plus B. Now by Lagrange's mean value theorem, so epsilon is a value between A and B. F dash epsilon will be equal to f of b minus f of a by b minus a, which means 2 capital A times epsilon plus b is equal to a times of b plus a plus b. From equating the two, equating this one and this one. Okay, so b cancels, then once b cancels, a also cancels, so epsilon will be b plus a upon 2 or a plus b upon 2. So this is just application of the mean value theorem. So mean value theorems are important, and more important than this mean value theorem is the extension of the mean value theorems. Cauchy's theorem we'll just go through tomorrow. We will not discuss this at length. We seldom we get a question, but we get lot on Taylor's theorem and Maclaurin's theorem. Okay, these two we will be discussing in tomorrow's class. Tomorrow's class we'll discuss Taylor's theorem, Maclaurin's theorem, some problems on that. Then we discuss monotonicity and maxima and minima. All right, and then we do a number of practice